Again, again. No, the last part of the lecture of 2. Posted. Okay, I will start a new slide here and I would write it here. Okay, so can anyone tell me Zoom again? Slideshow, I can write in slideshow. You sure? I prefer it here. I'm not used to writing in this one. This. Oh, yeah. Okay. So just let me draw something which we all know, CPU. And I'll tell you what each of these components are and why we do it after a minute. So in the CPU, for a question which we have to study, like, let me say first the CPU. The CPU has 3 main components for something that we are going to learn now. It's the program counter, the instruction register, and the accumulator. And in the Harvard architecture, how many memories do we have? 1 or 2? Okay, 1 for the instructions. So what would be the other one? The other one for there are 2 types of memory for the Harvard. They are the instruction memory and the data memory, 1 for instructions and 1 for data. If it is the von Neumann, it's like both for the same, like instruction and data is stored in the same. So this one follows the Harvard structure. Now, when the CPU requests for some information, it would go to the memory, usually like it would like to access the memory to get the instruction or the data. Okay, so this process of fetching the information or the instruction, and then it has to decode, and then it has to execute. So this is a cycle which we all see in this course saying fetching. Fetching is for the instructions. Decode, like instructions would be in some coded or encoded format. So we have to first decode it. So decoding the instructions, which is fetched, and then we have to execute the operations based on the decoded instruction. So execute operations based on decoded instructions. So this is the cycle that we are going to learn. It is called as fetch, decode, and execute. Now, these 3 things, the first one is the program counter. The program counter has one kind of role. The instruction register has another role. The accumulator has a different role. Now, what does the program counter do? It stores the instruction. What instruction? Address of the instruction memory. Okay, so who would be referring to the instruction memory? Who will have like where to go? The PC. PC stands for program counter. It's not the personal computer, it's the program counter. So in the CPU, the first component that we saw is the program counter. And what does it do, or what does it have? The address that it should go, and where it should go? In the instruction memory. Okay, now the IR. IR is the instruction register. So for now, we will just write what those are, but again, we will write the steps like with the numbers. So instruction register, IR, is the instruction register. And what does the instruction register do? Has the instruction which is fetched from the instruction memory, has the instruction fetched from the instruction memory. So just listen, it would be clear. If it's not clear, it would be soon made clear. Now, accumulator, what does it do? It holds or it carries the mathematical results temporarily. It holds the mathematical or some results. Is it clear what I'm writing, or it's just like too much vibrating? It's clear? I prefer the OneNote, to be honest. Okay, if it's clear for you, it's clear for me. If it's not clear for you, I will write it in OneNote. It's okay? Okay. Okay. Now, new slide. No, can I just go to OneNote if it's okay for you all? I'm not feeling okay. It's like too much scribblings for me. I'm comfortable with the other one. New section. Okay, add new note. Fine. Today's July 4, July 3, 3. Okay, better here for me, very better. So you see, it's much cleaner also. So we have the PC. Now we are going to the numbers. And now we have the two memories. You can see, I hope, yes? The two kinds of memories. In the assignment, it's the other way around. Like you have both in one, the instruction and the data. So for the data memory, let's put some address. It's random. There is no specific rule. It depends on the type of producer, like the manufacturer. For the educational purpose, let's just say like this is at 172, 173, 174, 175. This is 176, and it goes on. That's the address. Yes, that's the address. And this is the address of the data memory. And what's the other? The instruction memory. And let's put some address for that as well. So we'll say this is 06, 07, 08, 09, 10, and it goes on. Now, in the instruction memory, what do we have? Just the instruction. In the data memory, we can write and we can erase, we can store. So in the instruction memory, let's say in the 06, we have 0017. And we have, okay, wait. Let me put 0106. And then I have 02, 07, 03, 08, and 0400. So now I want to tell you what some of the numbers mean. 01, 02, 03, and 04. So here, after the 01, it can be anything. X means don't care. So after 01, after 02, it can be anything like 06 or 07. We don't care. Now, here, what does the 01 mean? It means load. 02, it means load. Let me check. Store, decode. 02 stands for decode. 03 stands for store. And 04, it is actually 0400. So this is the normal for the halt. Halt means stop. So 01 means load, 02 decode, 03 store. Now you will ask me if it is the same for all. No. For one processor or for one manufacturer, it's something. For the other, it is something. For this educational purpose one, we will just learn it this way. Now, this is the instructions, set of instructions. Is this much okay? This is usually provided, and this is usually what we will be doing for the examples with us. For us, 01 is load, 02 is decode, 03 is store. This would be given. For example, I have to, how do I minimize? So here in the slides later, you see the key would be given. Like 01 is load, it's add, sorry, 02 is add, 03 is store, and this one is hold. Did I say it different? I think I said store. It is add and then store. Sorry, it's not decode, it's add. It's add. So the first one, you saw it was marked in red, yes? They consider what is in the beginning. And don't care means they don't consider what is this, but this points to something. So let's see what it is going to be here. So we have the program counter. We have, what was the next thing? Instruction register. And then we have the accumulator. Okay. So let's see. We are going to see how it's going to work. So program counter, it would store the address of the instruction memory. Now we are going to start, and there is something more that I would be adding here. Some more of what the program counter does. So initially, if the program counter is having one of the address, let's see, it starts with 0.06. So if the program counter is 06, what is the instruction that it is going to fetch? 0106. So what does the program counter have? The address of the instruction memory. So we say program counter has 06 and it will fetch the instruction 0106. So what is this? Instruction fetched. So we are starting the process. So we are starting. We say initially the program counter has the instruction address. So it has the address of instruction memory. What does it do next? The instruction is fetched from that address. But where is it going to be stored? In the instruction register. So till now, is it fine? Okay. Now, 01 means, what does it mean? Load. So there has to be some kind of decoding now. So decoding, we do it this way. 01 load. But what does this 06 mean? It is the address. Now I have to make a change. Address of data memory. Now this address I have to change. Wait, let me make it. Now I have to change this. Just bear with me. Let me make it just 72, 73, 74, 75, 76. And in this, let me put some data. Let me put 0017 and 0023. So if I want to come to this address, I'm making it like 2 digits. So if I want to come to this address and I want to load this one, I have to give what? 0172. This 72, is coming from this one, load. You're smiling. Is it okay? No. Now I have to change it here. I cannot give this. I have to put 72. I want to fetch from the address 72, not 06. That was 72. So if I make 0172, what is it going to do? Load from 72, which is the address of data memory. So this is the decoding step. This is the decoding step. Now, what does it take from the data memory? What is inside? 0017. So where does it put the 0017? In the accumulator. So you see, we had like a process of the first step was PC having the address of instruction memory. It went to the instruction memory, iMemory, and looked for the address 06, found the instruction 0172, and then comes here. This is called as the fetch, or this whole thing we call as the fetch. It's like going there and bringing it. And then 01, we have the load. So it goes to the load, and from which data memory? 72, and the accumulator gets 0017. This is fetch, decode, and execute. It's not executing in full. There is like something we want to finish, but it's just like the intermediate step. We have more fetch, execute, decode, execute. Here we are just loading the accumulator. We want to do some mathematical operation. So there would be always the FDE, fetch, decode, execute coming in. Saying, yes, program counter has to be incremented now. As soon as, that's again, like it's going to be incremented, right? So just saying it again, look again. You have to understand this. So we have the three components which you are already familiar now, the program counter, IR, and the accumulator. We have the two memories, the data memory, and we have the one which is before that, the instruction memory, and we will have the addresses for that. So let's say, like as we said now, 06 or 07, 08, it can go, and this can be anything. So if you want to be like 82, 83, 84, any number. I'm giving another example. So here, program counter, what does it have? The instruction 06 that it should go to. And this instruction would say, fetch or load from the address 82 or anything. We are just saying 82. And 82 has 0032. And this one, PC would tell the instruction register, fetch the instruction. No, it goes here. It comes and puts back it here, 0182. So based on this 82, and based on this instruction, it does the decoding. It goes here, brings it here, 0032. And that would be the executing. Executing, and the first one is fetch. The second one was decoding. Decoding means, we cannot say that decoding there. This is the decoding. The instruction register decodes. Only then it will know to which data memory it should go. Yes. Say it again. Say it again. 0182 is the instruction. Yeah. Fetch is the data. This is the data. Okay, next question. What did you say? Okay. Okay, so we are actually starting from 0, 1, 0, 2, 0, 3, and 0, 4, 0, 0. We have not yet defined what that instruction is. 0, 1 means load what is in the, what instruction is in the specified one. So yeah, what load what data is in the, along with the this part, the XX. Go there, load it, and put it in the accumulator. So that's what Z01 says. Load what is in the XX and put in the accumulator. It can be anything. You ask again. Let me see if I cleared it out. Ask again. Yes.
The decoding starts when the IR calls for a location the data.
Okay, when IR gets 0, 1, 8, 2, it's the instruction. So it should know what it should do. So we are actually telling it, if the instruction, the first 2 bits is 0, 1, load. 82 means, but from where? 82 is the address of the data memory. 82 is the address of data memory. If it is not clear, you should ask. You should ask. No asking? So again, we have the next cycle coming in. Program counter we have. So I'm starting not from the beginning, but from almost the beginning, because we need the continuation. We have the accumulator. I hope we know what the first box is. Instruction memory. And then we have the data memory. So for now, you all are sure. Okay. So program counter, if it is like 0, 6, where does it go? To the instruction memory. And the first instruction for now, it is 0, 1, 8, 2. So this instruction comes back to the instruction register. 0, 1, 8, 2. So 0, 1, now it should know what it should do. So now it would decode. 0, 1 means load. 82 means like from where? It's the address of data memory, address of data memory. And it would go to the 82nd location here. And it says it has 0013 or some number. So now where does it put it? In the accumulator, it puts the 0013. It loads, 01 means load the accumulator. This much is okay. Now, as soon as the program counter does this up, let me put that in a different color. So as soon as the program counter makes this guy, the IR, fetch, so this is like the fetching of the instruction, fetching of the instruction. It would do, first it would do the fetch, and then it would do the decode, and then it's yet to do the execution, but it's like a kind of execution where it would load the accumulator, not full execution, but halfway. So you see, fetching the instruction, decoding the instruction, and executing the operation, which is kind of the load. What operation did it execute? But this is not the final one. We want the addition to happen. Okay, that's our final goal. For now, it's just loading, which is not our final executed result, intermediate. So what does the accumulator do here? It holds the intermediate result. It's not the final. We can say the accumulator holds the results, which is kind of intermediate also, and also it could hold the final result. But results which are intermediate. Let's see what we could do next. Now, the program counter has to be updated now. That's the next step. So this is the first step. Okay. So program counter has to be updated next. Now, there is something that we need to show in like 3 steps before the program counter gets updated. Let me show you. So this is very tedious. See, it's just the numbers that I'm going to write. Okay. Repeating. So program counter was initially 06. So with the 06, the instruction register was 0182. Yes. Then what happened? As soon as this becomes 0182, this gets incremented and the other operations are getting just continued. So accumulator becomes 0013. Now you see the program counter, once the IR fetches it, its part is done, it gets incremented. The later part it's happening, but the program counter is just like pushing it. Next is me, next is this, next is this. It just gets loaded while the other operations are happening. So it has the next instruction. So it's like the boss who is waiting to give you the next job while you are doing something. You should know that. The program counter, though it's updated, it's not getting fetched or not doing anything. While the other operations continue, program counter will have the next set of instruction. It already has the next work for you, even while you're doing your present work. It's like a boss. So that part is okay. This number update is fine. So while you're doing the next 07 job of fetching, this would already be incremented. Is that fine? Okay. Now we are going again to draw. You think like, am I repeating? Yes. Why? To make you understand. And at last, it would be a bunch of numbers. That's it. Now I'm not going to say anything. You know what the 3 blocks. Later, the 2 memories. We know all the numbers by now. Instruction memory, the data memory. And we have, what do we have in the instruction memory? The instructions. The data memory would have the data. And we have the instruction address, 09. And here we have like the 82, 83, 84, 85. It goes. So I'm writing here, initially the program counter was 06. IR would fetch the instruction, which is 0182. So IR would now become 0182. At that time, the program counter gets incremented. Now, the accumulator. I'm writing it as step by step. What does the accumulator will have? What is in here? 0013. The accumulator will have the 0013. Is this much fine? Again? Yes. Yes, the data would be specified in the question, or even you can put, I can put anything, any number. No, I can put any number as the address for the data. Like this can be any. This can be any. This can be any, not fully. Okay, what I have to match. This one has to be the from, yeah, this one has to be like 01, 02, 03, or 04. The others can be anything, but this has to point to this one. This is the data, any data it can be. It depends on the question or it depends on what you put. Okay. So I just want to show here the program counter increments as soon as it gives the instruction register fetches the instruction. Now, oops, did I click that? No. So now it did the fetching, the decoding, and the execution. It's done. So this step was the fetching of instruction. And here it did the execution. And here it did, I'm sorry, here while it did the execution, it actually did the decoding. Now we have to look to the next instruction. You see the program counter is ready to give you the next instruction. What is it? 00. Let me put 83. So there is some kind of data, any data. I'm just putting 27. So the next instruction as per the program counter is 07. And what would it be? Like what instruction is it going to fetch from 07? 0283. And what does our 02 means? 01 means load. Yeah, 02 means add. 03 means store. And 0400, it means the halt. So 0283, and by that time it does the fetching. This would have been 08. Okay, yeah. Halt means stop. Yeah. So program counter said that this is the next instruction. It fetched the instruction, and the program counter at the same time it got updated. Now what does it has to do? It has to decode. So what does it mean by 0283? 0283 means load. So let me write 0283 a bit detailed. I'm sorry, 02. Load. I'm sorry, store, add. 02 means add to the accumulator what you get from the address 83. Add. So what you already have in the accumulator, what is it? 0013. You have to add what you get from the 0083. So 0083 or the 83, what does it have here? 0027, and that is added to the existing content. So that is what is meant by the add. Questions?
If we add another, we go on to PC address 08 again, and we do adding again, then we will have the data will be from 0030. Okay.
Can you ask the question again?
So currently, after adding, what will be the data?
So, no, we are just fetching from there, adding in the accumulator. We don't add it in the data. We take the data and the result is kept in the accumulator. It becomes 0040. Yes. So this is kind of the execution. Like we decoded, we did some execution. What is it, the execution? It's just like storing in the accumulator. I'm like keeping in the accumulator. Accumulator is just a temporary storage. We cannot store it. So the next step would be the final step of execution where you can see. So here it is 02. 02 was to say add what is in the accumulator. 01 was to load, and the next instruction. You see in the 08, it is going to say 0384. 03 means you have to do the storing. Store where 84. What? This 0040. Now this would go here and it would be stored here. We load, we add, then we store. There is 3 steps. Load, add, store. Load using the instruction 01. Add using the instruction 02. Store using the instruction 03. So for each instruction, we have to go through the fetch, decode, execute. This is the core concept. Yeah. Yeah, we just add to it. No need to load again. Or we can even load and then, like, this is the best way. Load and then add to it. First load the first number, then add in the accumulator. The full okay, it's not the just showing the steps. So this is the initial, like program counter is at 06. And when this 06 is accessed, the instruction memory is accessed, you get the first instruction set. That's because as soon as the fetching is finished, the program counter is updated. The program counter doesn't hold the present instruction memory address. It's for the next instruction. The next. Yeah, that's what I said. It's like always telling you what's your next operation. It's not for what you're doing right now. Program counter holds the memory address for the next instruction. As soon as you do the fetch, the program counter gets updated. So program counter always holds the instruction for the next step, not for the current one. This is again the scribbling, the working. We would show or we would see the final clean result. But if I just show the final clean result, it would be a bit difficult to understand. Okay, so now we have the 0384, which says store. And what happens to the program counter now? 09, which is not the present program or instruction memory address. It's for the next instruction memory or next instruction memory address. It's not for the current one. The program counter always keeps the next instruction address. The present one you have to look up. So this is happening because of this one. You see 08 is this one. So program memory for this 09, what will happen would be in the next step. Program memory always holds the address for the next instruction, not for the present one. It's always getting updated. So now what is the instruction for this line? 03, store. What is in the accumulator? In the address 84. 03 stays store the value of the accumulator in data memory address 84. Address? Yes. Again? Well, for us, for all these questions, it will be empty. Okay. Well, that's a good question. Well, usually it is assumed to be empty unless stated otherwise. So here we would save the 0040 in the address 84. Why? Because that's what the instruction says. So we have like 0040 in the accumulator and it's now going to the address 84 of the data memory. So what's the next instruction? Like what do we have to do next? 09. Let's see. 09 says 0400, which means stop. Stop what you're doing. 0400. And we fetched and now we decoded and we understood. Halt. And we stopped. That's it. So when a question is asked, you would draw the first box. Oh, this lady is repeating. Yes, I am. PC, IR, A. Now I will write everything in one stretch. and it would be easy now. The instruction memory, the data memory. Now, question to you. For us, usually the key would be given. And what was the key for us? 0, 1, don't care, don't care. I want the girls to say this to me, please. 0, 1, what was it? I want to hear sound. Who will say? Okay. And what is 0, 2? Okay. Store, halt. Okay. So we have the key, we have the components, and I need the instructions for some, and I will also need like something to be in the data. So what we were doing was with 06, 07, 08, 09, and it goes. And this one was something like 82. We started with 82. Yeah, 82, 83, 84, 85. What was it? We had like 0017, 0023. Okay. Okay. 0013. Yeah. It can hold the same value. For us, yes, it can hold the same value. If it means halt means stop. Stop what you're doing. So it stops. If we want to clear it, we can also give the clear instruction. For us, the questions is out of scope. Like what happens with the accumulator? We can clear it with another instruction. For now, the accumulator is having something and we don't care. We care about the fetch, execute, and decode cycle. We can again create like another instruction, maybe like 05, if we want to create the key and say, okay, we will store it in an additional address. And when that address goes, we can make the accumulator empty. Well, it is possible to make the accumulator empty because initially it was empty. Okay.
But when you're storing a value from the accumulator, it does not produce value.
No, we are not giving that instruction. Okay, picture, we start. And 01, we say 82. The instruction, it is the instruction. The instruction says go to the 82. So it is with the instruction. Now we add with the something at 83 and we would store in the accumulator. The third step is like to store and the fourth step is to halt. So all this is coming from the instruction. And the instruction, how do we decode? Using the key. Now the program counter, it starts with 06. IR and A, and we will say what happens in the last line. What happens? Okay, so program counter is 06. So what would happen in the next step? IR goes to that, and I mean the program counter accesses the, yeah, and it would give this. So what is happening here? Fetching of instruction from instruction memory at the address 06. Is that fine? Okay. Now what will happen? As soon after this, it will become 07. Now the next step, 07, it is 01A2. 01 means load the accumulator. And the accumulator now will have this one. So what it actually did was decoding. It was decoding the instruction. And also what it does, it executed it. But there is no mathematical operation, just like loading the accumulator. And now we would do the what 07 says. Wait, where's my black pen? Okay, so now what does the 07 say? 0283. And as soon as it gives, this becomes 08. Now, what will happen in this? This is actually the fetching of instruction. Yes. And now 0283, we will have again 08. What is happening with this? Adding. And 0027 and 0040 is what the accumulator has right now. And this is again what happens in this stage, decoding and some kind of execution, not the final answer. I mean, this is not what we want. What we want, not just see, store. Storing is the final step. So now we are done with the 08. No, we are going to do the 08. So what does the 08 say? 384. So now the program counter gets incremented as well. And now we can write in one step. Yes. What happens? 0040, but this is going to the up. Reach. It would be stored at this point in the data memory, 0040. And now we are saying we actually stored in the data memory. And that was the final step. Do we need something more? No. So we would do this instruction now, and that is 0040. Well, this gets incremented again. This can, I'm sorry, 0400 it is. 0400. 000. It's not the result of the calculation. I'm sorry. The result of the calculation is 40, but the instruction is 0400. So now this comes here. Well, the program counter gets incremented. It's always like ready to give you the next task. This can stay. It's okay for us. But with this, there is just the fetching of instruction, and there is like the decoding of instruction. There is no execution, but because it is halt, there is no execution. I hope at least you have understood 70% more. Okay, now can I show you the crazy slides? Yes? Okay, don't blame me. It's supposed to look like that. So this is what the slides look like. Again, I will keep this is all for you to read, reading materials. I made it like reading materials. You can look at it, you can read. Well, I will keep the paper here and you can look at it when you get time. I will modify it again because I made like small typos while I wrote. I will put it properly during the break. Give me 5 minutes for me. So I will make it proper and I will upload it again. That's the end of lecture 2. And to say there is no break, that is the assignment 1. The assignment 1 kind of looks like this. So it's the fetch, decode, execute cycle. And you can go through that when it's posted. I'm sure it will. Don't take pictures. Don't look at it now. I'm just moving it. You can read it later because now we don't want to read it. We will read it a bit later. But it's from what you did right now. Yes. Then you will do it to like you will do.
Yeah, when we have.
Usually a posting or something is done like an assignment and you will have 7 days to solve, usually. But since this is summer, possibly it could be like 5 to 6 days because summer is meant to be faster. So, no, you will be given the introduction to that. Tinkercad we would do in the coming Tuesday because I want you all to do it with me. I didn't give the notification yet for bringing the laptops. So Tuesday, even though we finished the 3rd lecture today, we would have like a bit of the Tinkercad and the state diagrams, all those things on Tuesday. Fun, yeah. Yes. That's why there is like a time limit given. But yeah, for any question, you will have like 2 or 3 days left. Well, we have to have the exam one in the coming week, I think. Then your summer semester will like collaborate with the fall semester and they would put me in trouble. So hopefully it would be in the Thursday and we cannot complain like we didn't get enough of time. You are supposed to find time. Okay. You can open the Tinkercad and you can also log in and sign up and have a look at it, but the formal teaching would be on Tuesday. Okay, now we go to the lecture 3. It's very simple. Who's saying that? No, it is. Then why am I teaching it? So, lecture 1, 2, 3, and hopefully 4 also. I'm making it simple. You should see the old lectures, how the professors make it. It's like too difficult. For me, I'm making it just the essential part, but you cannot reduce more with the essential things. Okay. So you might have seen diagrams with where you draw the round and you put some numbers, you connect them. You have seen flow charts. Yes? Yes? Huh? No? Who says no? No, we have at least seen one time anywhere, at least, because I think you are doing your 3rd year or 2nd year, at least 3rd year. Yes? So you might have seen. And why do we need a flow chart? When do you usually draw it? Yes, to make yourself understand. Yes, or you like tell someone, this is how it goes. It starts, it will have the diamond boxes, it would have the squares, rectangles. So it's like easy for you to understand. And it's like you draw how the process is. Yes. So another version of those flowchart is the state diagram. State diagrams, we will have circles with the numbers 0, 1, 0, 2 written around it. Well, when we come to the flowchart, it would have special shapes, oval, rectangle. So those are some kind of diagrams we would be seeing in this chapter. And it's not difficult because if you understand the problem, you can solve it using any of the state diagram, any 2 types. The bubble one or the flowchart one. The bubble one is with the circle, the triangle one, the rectangle one, all those shapes comes under the name flowchart. Saying it very simple. Now, this one, you see, it's written here. Why do we need it? Like to model the behavior. So any problem you have, you can draw or solve that using the state charts, which you in a more professional way, you can call it by the name state machines. Now, why do you call it finite state machines? Because it's having finite number of states or operations or chances. Like for example, when we beep a horn of our car, how many states does it have? Beep, 2. Yeah, beep on or beep off. Or when you have a switch, normal switch, you have on, off. But there are some switches like on, middle, and off. So it's like you don't have like infinite state, but like a countable number, finite. So that's why they say it like finite state machine. You can also call it state machine. And automation, because like any big process, you can simply show it like a diagram. Like some big manufacturers or big cases, you can just easily show it with a diagram. So these are the alternative names, but why do we do it? For modeling. What are we trying to model in this course? Some embedded system, some IoT device, yes? So we need to know it. Now, for any problem, we need to know, for us, for this course, we need to have some sensors, some actuators, some outputs. There would be some LEDs, and we need to know what would be the different states in between. For example, again, the switch cases, like we had in the other room, in any room, like for the projector, we will have like 6 or 8 switches. And we know, like, if we press that, this will happen. If we press this, this will happen. If we press both of them together, something else will happen. So that is the third step. Like, we should know what are the different states or conditions of the system. And finally, we can develop a big diagram to show, okay, from this, it would go here. From left, it would go right. So that's how we come to the solution using this state machines or diagrams. Now, again, like if it is a toy, yes, you might have seen kids' toys. We have like many buttons on, off, but when it comes to a phone, the same button can do on and off. So what does it like look like? So a machine whose output behavior is not only a direct sequence of the current input, but has some history of its inputs, which means we will see much detail. It might look like not much sense, but we will see the examples again. So there are some systems who has memory, and like you have a memory. If I tell you something, you might say, no, I don't think so. So you will have your own memory and your input to decide something out. So, but this one, it's like the phone is on, you push the button, phone is off. So this is a simple example of two states, on and off. This diagram you can draw not with the square boxes, but with the circle. But this is AI generated. To be very honest, I didn't get time to draw. So instead of the square boxes, you can draw circles. That's the most accurate way of doing. Okay. So when the phone is off, if we press the switch, what will happen? The phone turns on. So I can draw again, 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 again. But what is the easiest way to draw? The side flick. So this is another way of saying the operation of a phone. So you see how you modeled it using a state diagram. Yes, you don't have to say in words like when I press the switch. No, no, no. You can easily show the operation of any device using a state diagram. Looks simple, yes? Now, what are the different components coming for this kind of operation? There would be like states, which is set in the circles or in the boxes. There is like connecting arrows, which shows like the transitions. And there is also called as events, which we will see now. So event means like if you are in a state, like I'm being happy, something external happens and it changes my state from happy to being sad. So external trigger or events might happen in the state diagram. So external inputs, or it can be a trigger which could change the state. And what do you mean by the initial state? Sorry, the first state. So that's the first state. So initial state, the transition, it's just have the initial state, the intermediate state, the final state. And these lines shows the transitions from one to the other. Now, what is the trigger here? Switch. What is changing the state? The switch. Okay. Who gives the trigger? The switch. I'll give you the difficult PowerPoints if I'm not sure if you would gain information from that. So I will keep the original and the symbol one also. So this is the symbol. Now, this is what I said in the beginning. There are like two kinds of representations using the bubbles, which I will show now, and using the algorithms. Algorithmic state diagrams. It's the flow chart. That's the simple way to say it. And there are like two kinds of the state machines also, Mealy and Moore. It could be, I will show you. So this is the state diagram, the bubble diagram, and this is like the flow chart. So you see the state diagram is always having circles and jumping lines from one to the other. But when to the flow chart, it would have those specific shapes of specific purpose. You know why we use the triangle? I mean the diamond. It's like decision. It,
There's more than one possible outcome.
the circle is the initial one, the first one. This one. This is the initial. Okay. This one, where we see this one, you see how we output it as 3. So it's like the decision box. It could go here based on one decision. It could go here based on another condition. It could go here based on another condition. So this is something with the butterfly. So if it hatch, it becomes the butterfly and then it goes to the death. If it's like eaten by a snake, also death. But if it is crashed, also death. So this is like the decision box. It has like many conditions of output. And what is the next box after the decision box? You see the rectangle, rounded rectangle. So this shape, you see, after the decision box, you will always have the rectangle as the output. We can say it's the rounded rectangle where the edges are round. So we start with this symbol. The initial one is always a circle, or we can keep it as an oval. The starting one, when you see in, you can search again for the others. I will also show you. The starting one is usually oval or circle. This before and this after is usually the rounded rectangle. You cannot put like, I like this shape, let me put it there. No, it has to have a structure. And again, you see the decision is having the diamond, then the rounded rectangle. Even from there, it is the rounded rectangle. The stop one is this one. You can either the circle or the oval. You can keep it as the start and the stop. The start and the stop have the same shape. Okay, I will show you further examples. Now, there are 2 types of state machines, Mealy and Moore. So one of them is good for one application, the other is good for the other application. Let's see. Now, just a symbol diagram here. You see which of them has more circles or more states? More. And which has less? Mealy. So we can just look by saying that Moore has many number of states. It's simple, but needs more components. That's something that we could just say by looking. But for now, we can say it has more states. It is simple. It's just like one over the other followed by the other. While in Mealy, you will have lesser number of states and it's complicated. For now, that much of information is enough. And we will have a bit more look into the Mealy and Moore. We'll come back from here. So let's read what it's here. Moore outputs are functions of the current state. Read these 2 lines only. Outputs are functions of current state. Well, Mealy outputs depend on the state and on its inputs. So outputs change synchronously with the state changes, while this is asynchronous. So Moore means it depends just on the present state. It doesn't depend on the input. So you could research on this further, and you can go crazy. For now, just understand Moore. Moore means it just cares what is the state now. While Mealy, it cares about what state is coming to it and also the input. So you see, input changes also affect the Mealy. For Moore, it's just the state. For now, let's see what it is and we will see the practical examples further. For Moore, it just cares about what state is coming to it. While Mealy, it also cares or it also looks into the input. So Moore is supposed to be synchronous. Mealy is supposed to be asynchronous. It will make sense as soon as we see the examples. Okay. Now, we know this already. We have an input, we have a state, and then it would cause a transition to the next state. This is very simple. Okay, now the complete one. You see, the circle one, this is called as the starting. Remember, this is AI generated, and actually the state diagram has to be in the circle shape. Okay, so the initial state, this is also a state diagram, but for to make it like the technically sound one, follow the circle shape. So this is the starting point. You see, it's the initial state marker. And states, how many states do we have in this complete state diagram? 2. And what does the arrows show? The transitions from one state to the other. So this is the initial state. You transition to the state 0. Then from the state 0, you transition to the state 1. Is that okay? Now, you see arrows show transition between states, labels on transitions. So we should put the labels also. You see how many labels do we have on the transition? This is a transition. IN1 means input 1. And what is this transition lines marker or label? IN0. What does IN equal to 1 mean? Your input equals to 1. So we can say that in a sentence that when state is 0 and you give an input, your state goes to 1 and your output is 1. But when your input is 0, you go back to the initial state. So this is all preparing you. This is all preparing you to make a general or the practical example. For now, you have to know that there can be more than one state. There could be a transition from, there is a transition line, which is like an arrow from one state to the other. And there should be some transition label also, because we should tell it what is causing the transition. Transition or the trigger, like what is causing it to change from one state to this. So when the state is 0 and you give an input, the state changes to this. And when you are in a state 1, you will have an output 1. And now when the input is 0, you transition back to the state 0. This is just base theory. We will see the real application soon. Now, visual elements, like what do you see in a state diagram? The circles as states, the arrows as the transitions, and you are supposed to put the labels like the IN, the output, that you are supposed to maintain that. Now, okay, like you have a switch in the car to turn your horn on, or you press it, you hear the sound, you take your hand off. How does the car horn work? You press, you hear the sound, and then you take your hand off. It's not the same like the switch here. You press, you get the light. No, each of them have different operations. So let's see this example. A car horn. It's quiet when you don't press. But when you press it, you hear the sound. So there is no complex processing. It's like just you press, you hear the sound, and that's it. While when you have a room light switch application, when the light is off, you put the button or press the button, you get the light. And when you turn it off, it's off. Now, who has to have some memory of what is happening? Like light can't forget. Even if we switch on and switch it off again, the light cannot just stay like that. So there has to be like kind of memory or simple memory for the case of light or switch. So you see here, the last two lines. Horn means symbol input, symbol output. There is no need for it. While this one, we call it toggle. Toggle means it should remember the previous state. There is like the light application, like a room light switch example, and the car horn example. In the car, press, hear the sound, take your hand off, finish. While when we come to the room light situation, it has to remember its previous stage so that we get the proper output. So these are two examples, and let's look at the next slide. What the next slide says. Okay. So for saying something. Well, I'm complex. Okay. So melee means action on transition. So look at the title of the slide. We can take actions, or the state machine can have some actions. Like when the actions can happen when it is transitioning or after the transition or after the trigger. So see the first one. The horn is quiet. That's its state. You do the transition, you hear the sound then. And when you take your hand off, it's quiet again. So when you give the trigger or when that transition is happening, you see the action. But again, when you take the hand off, there is no sound. So press, hear the sound. When you give the trigger, you get the action. But when it comes to this one, the action is in the state. The action is happening in the box. So that one, the action is happening in the transition, while when it comes to the mover, the action is happening in the state. These are the two key differences that we need to understand. The actions by the state machines can happen during the transition or within the state. Is it making sense? Okay. So when does the horn sound? During the transition. When does the light stay on? After the transition, during the state. And that's how now we come to the melee and more key difference. Melee means action happens during the change, while more action happens while in the state. So melee means action happens during the change. That's the key thing that you need to understand. Melee means you can just have the change happen during the transition or during the change, while more means action happens while you are in the state, during the change and while in the state. Is it okay? You can understand? Yes? Now, so let's look at the headings again. State diagram. We were just saying about the state diagram, and then we said like the actions can happen during the transition or when it's in the state. Now, we are just adding some capability to it. So we call it by the name extended state machines with variables. So it's like we want to add some more advanced features to it. So car horn example, we said it's melee. The transition or the action happens during the transition. And it said clear here again, like press the button, honk. What will happen? We are just like adding a variable. Variable means some math to it. So let's define the variable called as count. So one time you press the button or the horn, the count increases to 1. Now you release the hand, it stopped honking. Now you press the horn again, the count becomes the initial count, what you had, plus 1 again. So it is like initially there is no horn. So what variable you define? Count plus 1. So initially there is no horn. You press it once, what will happen? The count value will be 1. Now that is stored here. Now when you press again, it would be the initial value plus 1. Now you have 2. Now you press the next time. The count would be this value plus 1. So it goes like adding up. So like, have you heard like when we buy some lamp, or some switches, say switches. Does it say like you can press this switch until 5,000 times and after that you won't be able to use with that much of efficiency? Have you seen something? Well, I think I have seen it somewhere. So there are some counts, or they say you can use this thing this much number of times, after which it decreases the efficiency. So adding such kind of variables will help us in analyzing many things. So if you are a driver and you have such a count, so while you are going in a traffic street, you're honking the car 10 times. In a normal day, you're like, no, I'm having time. So can we use that to assess your behavior?
It's
Yes.
word that you have, word that you know.
The more that you're mad, the more you honk. Yes. So this variable, if we add such variables, if we add to the state diagrams, it increases your efficiency in some kind of calculation, some way or the other. So now here, again, we have the changes happening in the state. For that one, changes happening in the transition. Now for this one, this example you see, when we turn on the switch on this much number of times, it's actually making a count there. And we can count like how many times the light has been turned on. So it depends on your project. When you do a project, you have this capability, like you are drawing a state diagram to show, okay, this is what I'm trying to design. And you define a variable saying count or saying something else more count, and then you can say the speed. So if you add some variables to it, the state diagram would be more meaningful. Like you can just draw a person without eyes and mouth and just say, okay, that's a person. No, you have to add the eyes, the hair. So you're adding variables which makes meaning to the diagram. So you have to have variables. So you see, if we add count to it, we can count how many times the horn has been pressed and we can track the usage. So for your kind of application that you develop, you can define many number of variables. This is just like one. So imagine you are defining or developing an embedded system and somebody is asking you, the question is like, draw the state diagram. You will just draw this with this and this. It doesn't make sense. You have to add more variables to it. So this is just something very simple. You can add more features or variables are some kind of features that you add. Same way for the light. If you count how many times the light has been turned on, you can use it for energy monitoring. So you see, as many variables you add to your state diagram, you are bringing up new capability to your system. Okay. So 3 o'clock, we'll have a break, but don't go. Please take 5 minutes to write your name. I don't have a paper, I'm sorry today. I'll be nice from the next week. Please write your name. Girls, find a paper, write your name. Boys, please find, oh, okay. He doesn't want the idea. The most difficult also finding which can we have to be oh, she's running. So we will run to the next one. I will come with that. I have the other that is like one in I. So it's us like we have to do it in the same time. Everything same days. If she says I want it to be on Thursday, if she also wants it to be on Thursday, let's see. Hopefully, it would be like the assignments would be done by the end of the day. Everything will have a clear picture. We are not able to meet. Okay? We are running away after the week every day. We are not able to. As soon as we meet today, it's a class, okay? And we'll meet in this. Answers without transferring. Yes, yes. I think as soon as the, yeah, it's, yes, that's a good idea. So maybe I'll give like 4 days, 5 days for the assignment submissions. And by the end of deadline, I will give 50 orders. So that's the better. That's a good point. Okay, let me. Yes. Yeah, I'm learning with you. So you can come back at 3:15, 3:20. By that time, please be back. Yeah, 3:15, 3:20, not later. Yeah, break. Yes, yes, please. Just go after you finish that signing the writing your name. Thank you.
I submitted for chapter one of Word document with like all the things. And I took notes from my notes, but they took notes. And then to the second chapter, I submitted like 3 pages. So is that not together for more?
You submit, like, usually the last attempt is graded. Okay. If you can combine and send them again, because you have time until midnight.
Yes, I have to.
So you can combine and submit. It's good.
I submitted, but I don't know what get the homework. I submitted one. I have
Like two attachment or one
two
attachment
attachments.
at the same time.
Yes,
Then it's fine. It's
so I'll get the homework.
hopefully yes. Why do you doubt?
Because I want to get a good mark in the subject. That's why.
Hopefully, if I see something missing, I'll let you know.
Okay, thank you.
دكتور عن لا تقتصر ستنا
Yes. GCM, yeah. F is equal to 2 pi F. Yes, it's correct. Yes. 1, 2 pi. Yeah, it would be okay, so it's 11/2 into 2 pi. Yeah, 11 pi. Yes, yes.
النص النص
The break.
Yeah, till 3:20. Yes. Thank you.
അല്ല അത് ജസ്റ്റ് ഫിഗർ ആണുള്ളത്. ആ ഫിഗർ ജസ്റ്റ് ഇന്റർകാർഡ് ഓപ്പൺ ആക്കുക. എന്നിട്ട് അതിനകത്തുനിന്ന് ഒരു കോഡും അതിൽ കൊടുത്തിട്ടുണ്ട്. അപ്പൊ കോഡ് കണ്ട സ്ഥലത്ത് അത് കൊടുക്കുക. കണക്ഷൻസ് അതിൽ നോക്കി കൊടുക്കുക. ഏജ് കണക്ട് ചെയ്ത് കണക്ട് ചെയ്ത് അത് ജസ്റ്റ് അതുപോലെ തന്നെ കണക്ട് ചെയ്താൽ മതി. ആ കോഡ് അതേപോലെ പേസ്റ്റ് ചെയ്തിട്ടുണ്ടെങ്കിൽ നമുക്ക് സീരിയൽ മോണിറ്ററിലോ നമ്മുടെ ബാലൻസ് കാണിക്കില്ല. അത് അതിന്റെ എക്സ്പ്ലനേഷൻ വായിച്ചു നോക്കിയാൽ മതി. ഇത് ജസ്റ്റ് നമ്മൾ ഇൻപുട്ട് വോൾട്ടേജ് കൊടുത്തിട്ടുണ്ട്.